Okay, this is lesson 16, the converse of the Pythagorean theorem. And this is a topic that we first touched back in module 2, I believe lesson 15. And we're going to revisit it here. We didn't actually do a proof of it, we just used it back then, but I encouraged you to look at the proof of it. So today we'll look at a fairly straightforward proof of the converse of the Pythagorean theorem. But first, let's just review our proofs of the Pythagorean theorem. So we've done 3. And so back in module 2, we did this proof. Oh, this was module 2, lesson 15. So the converse must have been lesson 16. But anyway, this was a proof from congruent triangles, which I'll talk about in just a minute. But first, let's just review the proof from similar triangles. Centered around starting with a general right triangle with sides A, B, and C. And we proved by looking at ratios, we proved by dropping a perpendicular here in this triangle, calling this point D. Oh, that doesn't look good. Calling that point D. Myself a little more room here. Right here, the point where it dropped down to a perpendicular. We created 3 similar triangles. Our original one being one of the triangles, and then these other 2 translated and rotated and reflected to be in line like this. So you have to kind of, in your mind, imagine where they first came from. Looking at the ratios, because similar triangles, the ratios of corresponding parts are going to be equal. And so we were able to show that a squared plus b squared equals c squared by doing that. So you can look back at that proof if you need to. We've done that one a couple times. And then we used some of the results from this to create a proof of the Pythagorean theorem based on area models. So in other words, this area here off of leg B is b squared. The area off of leg A is a squared. And we were able to show that these 2 areas do add up to the area off the hypotenuse, which is c squared. So that was another proof using area. And it was very similar to this proof, and it used some of the results in order to be able to do it. So there is an additional video in the playlist that we've watched a couple times. We watched it in class, and you can watch it again. It's a silent video, but it's very visual and walks you through it again. So you can look at that one. And then this was the proof we did back in Module 2, Lesson 15. And it's based on some things we know about triangles. So here is these are 4 copies of the original right triangle, just the general one with A, B, and C. So it was given that these were right angles, okay? So we put these 4 triangles together. And one of the things, you could go back and look at this proof if you want more detail, but what we noticed was that this angle here and that angle were from these triangles here. So because this is 90, these 2 angles have to add up to 90. So when we put them together right here in a straight line, we notice that these all have to be 90-degree angles. So what we have here is we have here a big square with side lengths A plus B, and we have 4 copies of the original triangle, and we notice that this is indeed a square in the middle. So we've proven that this is a square. It's not a parallelogram or anything like that. It's a square with side length C. So this area here is c squared, all right? So if you look over here, we can rearrange these triangles. They are congruent triangles, correct? So we can put these 2 together here. This is side length A and A, so this is a squared. This is side length B and B, so this is b squared. So what you notice here is these 2 big squares have the same area, if we take away the 4 little squares from both of these, then we're left with c squared, and we can see that this area here, c squared, has to equal the sum of these two. So I think that's a really great visual. And so here's 3 proofs of the Pythagorean theorem, and they're not the only ones. There are more. You can look on Khan Academy for a couple more different proofs of the Pythagorean theorem. So, but what we're going to look at now is what we mean by the converse of the Pythagorean theorem. So the Pythagorean theorem says that if we have a right triangle and it has legs A and B and hypotenuse C, then a squared plus b squared equals c squared. So if we have this right triangle, then this relationship between the sides of the triangle holds. And that's really important and useful because if we're missing one of the lengths, we can solve for it. Okay, so we've done that. The converse of the Pythagorean theorem, and we talked about this back in Module 2, is kind of the opposite. So notice I used orange for this part and green for this part. So the converse just flips those around. It says if we have a triangle with sides A, B, and C, C being the longest side, and it satisfies, the side lengths satisfy this a squared plus b squared equals c squared. So we're starting with knowing that this is true. Then we know that the triangle is a right triangle. Okay, so if we have the a squared, we don't necessarily know the angles of our triangle, but we do know that a squared plus b squared is c squared. Then we've proven that the triangle has to be a right triangle. Okay, so there you can see would they be useful in different settings. So that's the converse. So, and this is back in lesson 2. We don't always know with these if-then statements that we can turn them around like this. And the example I used back in Module 2 was one of if it's raining, then the grass is wet. Okay, so that's true, right? If it's raining, the grass is going to get wet, unless there's a cover over it or something, but assuming there's no cover. If it's raining, then the grass gets wet. The grass is wet. But if we turn that around, it would say, if the grass is wet, then it's raining. Which isn't necessarily true, right? It's not always true. There's a lot of other reasons why the grass could be wet. We could be watering it. So when you have a theorem like this, you can't always just flip it around. You have to prove it. And so that's what we're going to do now. We're going to look at a proof of the converse of the Pythagorean theorem. There are various proofs of this. We're going to do one that is based on congruent triangles. So we're going to have to do some basic rigid motions here. So we're going to review a few things. Okay, so we're going to start with, I'm just going to talk through this. So if you look at these 2 triangles here, they're labeled, they're the same. They look fairly much a lot the same. But notice in this first triangle, we don't have this labeled as a right angle. That's what we want to prove. So we want to prove that angle ACB equals 90 degrees. That's what we want to prove, okay? But we know on this one, we know that a squared plus b squared is equal to c squared. So that's what we know about this triangle, okay? All right, and in this triangle here, the second triangle, A prime, B prime, C prime, triangle A prime, B prime, C prime, we know different things. And this one, we know that angle A prime, C prime, B prime is 90 degrees. but we don't know this relationship about a squared, b squared, and c squared. I mean, we don't know that this is what this length is here. Okay, so we're going to look at the second triangle here, the a prime, b prime, c prime. So since we know that this is a right triangle, then we know that a squared plus b squared equals the length a prime, b prime squared. Okay, so notice, I don't know if I was clear about this, but we've set these triangles up so that the A and B are the same on both triangles. But we don't know that this is a right angle yet, okay? But we do know, like I said, that a squared plus b squared is c squared. So what we know now is that a prime, b prime has to equal c, right? Because a prime b prime squared is going to have to be equal to c squared. These two things have to be equal because a squared plus b squared is c squared here, okay? So this length here we now know is c. Okay, so what we know now is that these two triangles have identical side lengths. This one has a right angle. So what we're able to do then is we're able to use some basic rigid motions like a translation to translate this triangle right over on top of this one. Since the side lengths are all the same, we've shown that this side length has to equal c because it's a squared plus b squared, and we know that that is c squared. So when we translate this over, we might have to, whatever the basic rigid motions are, we can map it directly on top of this triangle. And since the rigid motions are degree preserving, we have shown that angle C has to be the same measure as angle C prime. And so therefore, our triangle that we started with here is a right triangle. So that's kind of a discussion proof there of the converse of the Pythagorean theorem. So again, remember the converse says we know that a squared plus b squared is c squared. We have these three lengths. We don't know that it's a right triangle, but what we've shown is that if we know this, then we can know that it's a right triangle and that the angle opposite the longest side is going to be 90 degrees. All right, so let's look at some exercises then. Exercise 1 says, is the triangle with leg lengths 3 miles and 8 miles and hypotenuse of length square root 73 miles a right triangle? Show your work and answer in a complete sentence. Okay, so we could, we could draw this up if we wanted to. We've got kind of a short leg, a longer leg, and a longest leg. Square root of 73 is our hypotenuse. We know we know square root of 73 is greater than 8 because 8 squared would be 64. But let's just write up this relationship. So we've got a squared plus b squared equals c squared. We're checking to see that that's true. If that is true, then we know that this angle opposite the hypotenuse has to be 90 degrees. Okay, so we'll call a equal to 3. So we have 3 squared plus 8 squared. And we want to know, is that equal to the square root of 73 squared? Okay, well, 3 squared is 9. 8 squared is 64. And what's the square root of 73 squared? Well, the square root of 73 is that number that I multiply by itself to get 73. So when I square it, I get 73, right? So square root of 73 squared is 73. That's going to be really useful to you. A lot of these problems are going to have square roots in them, so you have to know how to square a square root. But it's pretty obvious when you think about it. So 9 plus 64 is 73. That is equal to 73. So we could say the triangle with given leg lengths, I'm answering a complete sentence here, is a right triangle. And I could say, I know that by the converse of the Pythagorean theorem. Okay, so we didn't know how to write angle, but because we showed that a squared plus b squared was c squared, then we know it's a right triangle. All right, so what is the length of the unknown side of the right triangle shown below? Show your work and answer in a complete sentence. All right, so let's call this missing leg length x. We know we have a right triangle here because it's labeled as a right triangle. Remember, it has to be labeled. It can't just look like one. But it is labeled, so we know that it is. So what we have is that 4 inches squared plus 1 inch squared is equal to x squared. So we have 16 square inches plus 1 inch times 1 inch is still just 1, but it's inches squared now. 1 inch squared is equal to x squared. So I'm going to turn this around. X squared is equal to 17 square inches. And so if I take the square root of both sides, the square root of x squared is equal to the square root of 17 inches squared. So the square root of x squared is x is equal to the square root of 17, and that would be inches now because the square root of inches squared is inches. So x is the square root of 17 inches. That is our exact answer. To find an approximate answer, we're going to need to figure out what the square root of 17 is. So my starting place is 4. It's going to be really close to 4 because 4 squared is 16. So I can start trying, I can start multiplying out. I can take 4.1 squared, and I can see which is the closest, 4.2 squared, and so on. I might need to check a few others. So let's check those with a calculator. Let's use a calculator on this to get to the tenths place. Okay, so I did this on my calculator. 4.1 squared is 16 and 81 hundredths. 4.2 squared is 17 and 64 hundredths. So I know now that my answer, the actual value of the square root of 17 is between 4.1 and 4.2. I don't even need to do this one. It's between 4.1 and 4.2. And since I only need this correct to tenths, I can decide, is it going to be closer to 4.1 or closer to 4.2? And I can see that 17 is closer to 16.81 than it is to 17.6. So my approximate answer would be 4.1. So x is approximately 4.1, correct to the tenths place. So there's my exact answer, square root of 17, and here's my approximate answer. Okay, problem 3 is very similar. We can write out our relationship. I'm going to leave the units off of this one just for space. We know that 2 squared plus 6 squared is equal to c squared. We'll call this c this time. So this would be 4 plus 36 is c squared. So c squared is equal to 40. So c is going to be equal to the square root of 40. I'm shortening this, okay? You're going to see worked out examples where when we know that something squared equals something, we know we can take the square root of both sides to find that x to the first power. Okay, so that's what I've done here. I've taken the square root of both sides and come up with c is the square root of 40. All right, so remember in our simplifying these radicals, we want to take out any perfect square factors. And so we can kind of see in this one, because 40 is equal to 4 times 10, that's a perfect square there. And so we can rewrite this as the square root of 4 times the square root of 10. So c would be 2 times the square root of 10. So that would be its simplified form. Both of these, square root of 40 and 2 square root 10, would be exact answers. But the second one is preferred because it is simplified. Okay, so now we want to find an answer rounded to the 10th place. And so I'm going to go back to the square root of 40. So the square root of 40 would be close to, well, it would be between the square root of 36 and the square root of 49. So it's between 6 and 7. So we're going to start maybe trying, I would start with 6.5. Well, is it closer to 36 or closer? It's closer to 36, so it's going to be closer to 6. So I would start with maybe 6.2, 6.3, checking these squares. And we might need to check one more. So let's look at what those are. So do those on your calculator and see what you find. Okay, so I punched them out on my calculator and got these values for 6.2, 3, and 4. So we can see that the actual value of square root of 40 is going to be in between 6.3 and 6.4. So it's a little bit bigger than 6.3 and less than 6.4. A lot closer to 6.3 though, 39.69. This one's all the way up to 40.96. So our closest value for C would be C approximately the square root, or not the square root, but approximately 6.3 would be our approximate answer for C. Okay, look at exercise 4, and I think this one you could try on your own. And let's see, and exercise 6 as well. So, so go ahead and work on those and then come back and we'll check them together. Okay, so to check if this is a right triangle, we're going to just check the Pythagorean theorem relationship. 9 squared plus 9 squared. We want to know if that's equal to the square root of 175 squared. So this would be 81 plus 81. And this over here would be 175. So this would be 162, and that is not equal to 175. So your complete sentence answer should say something like, the triangle with the given leg lengths is not a right triangle because it does not satisfy the Pythagorean theorem. Okay, so let's look at the next one. The next one is a triangle with leg lengths of square root of 28, 6, and a hypotenuse of length 8. So we would have the square root of 28 squared plus 6 squared, and we're checking to see if that's equal to 8 squared. So this would be 28 plus 36, and we want to know if that's equal to 64. And we get 50 plus 14, so that is 64, is equal to 64. So this one checks out. So our complete sentence answer would be, a triangle with the given leg lengths is a right triangle by the converse of the Pythagorean theorem. All right. All right, so now work on exercise 6 and 7 on your own. 7 presents a little bit extra challenge. You have to remember what an isosceles right triangle is, so see if you can figure that out from the diagram. Assign variables and work on that. So work on those and then come back and check your work against the video. So for problem 6, it is the hypotenuse that's missing because we know it's the side opposite the right angle. And so our relationship that we're working with here would be 3 squared plus the square root of 27 squared. We know that's going to be equal to c squared because we've been given that it's a right triangle. So we've got 9 plus 3 squared is 9. Square root of 27 squared is 27, and that's equal to c squared. 9 plus 27 is 36. And so they've made this one easy for us because the square root of c squared is equal to the square root of 36. So c is equal to 6. And your complete sentence answer would be the length of the hypotenuse of this right triangle is 6, and let's see, our units are feet, so we would want to include units there. The hypotenuse is 6 feet. Okay, I didn't write out the complete sentence, but you should have. The triangle shown below, let's look at number 7. The triangle shown below is an isosceles right triangle. Determine the length of the legs of the triangle. Show your work and answer in a complete sentence. So when we've done these problems before, we're usually only missing one length so that we can solve for it. We can be missing a leg or the hypotenuse. But if we're missing 2 sides, then we might have a problem. But this problem is a little bit different because in an isosceles right triangle, the side lengths are equal to one another. So I know I can use the same variable for both side lengths, and then I only have one variable to solve for. Okay, so the Pythagorean relationship would look like this. We'd have x squared plus x squared is equal to the square root of 18 squared. And we know our answer is going to end up in centimeters. So x squared plus x squared, if we have, basically we have 1x squared plus 1x squared. So this is 2x squared is equal to the square root of 18 squared is 18. Okay, so I can use properties of equality now. I can divide both sides by 2, and I'm going to get that x squared is equal to 9. Okay, so since x squared equals 9, then the square root of x squared is equal to the square root of 9, which gives me that x is equal to 3. So the legs are 3, let's get our units, centimeters long. Okay, so the legs of this right triangle are 3 centimeters long. So this is a special circumstance that allows us to solve for both legs, but it's only because they're equal. Okay, so let's summarize. You saw a proof of the converse of the Pythagorean theorem, and this theorem says that if we have a triangle with side lengths a, b, and c, and a squared plus b squared equals c squared, then the triangle is a right triangle. And so we proved that, and then our examples focused on the use of the converse of the Pythagorean theorem and also just the use of the Pythagorean theorem. Okay, so good luck with that problem set. You're going to be asked to restate a proof of the Pythagorean theorem and the converse. So, I would encourage you to go back and review those proofs and until that they become very familiar to you. Again, nobody expects us to come up with those on our own, but it is a really good exercise to be able to understand a proof that someone else has written.